and creation of new one. In the service case, these changes only cause movement of the beam, because when you change this spot are moving, right? But it's still intercepting the rod, whereas in the 3D case, you will miss it totally in that case. Okay, it's a little bit detailed, but in case you come across it again, you may remember, hopefully you remember a little bit about this, our discussion here. We can index diffraction ring reference. So the other point is that you can index or label the diffracted beam reference to the substrate space and receiver lattice, just like what we had 1110 or 2011, this sort of thing. And in the case of lead pattern, you are given this HK index, right? And they are, if you see weak diffraction spot, so first of all, you always identify the bright diffraction spot. Those will be your integer diffraction spot. Those will be the substrate spot. Those are the bright one. So you indicate HK, so 10, 11, 2 zeros, and so forth. And then you look for the weak spot if you have overlay, or you have reconstruction, or you have absorbe. The weak spot will usually be in the fractional spot, because these overlay structure are usually larger, the unit cell are usually larger than the substrate one, and therefore you will see it within a single residual space, because of course the length is 1 over, so you have something greater in real space, you will have something smaller vector in this real space. Okay? So in our individual spot, we indicate by weak pattern indicate by this, corresponding to momentum transfer with this HK. Okay, so something you may come across is that the center rectangular Perfetti length is a little bit trickier, because sometimes you see missing spot. We'll get back to this point. There's a little bit of fine point about this. So this point here, we talk about in the case of absorbe additional half order, what I talked about just now, half order or fractional order spot, right? These are the weakest spot, are usually found in residual space or lead pattern. So the residual space pattern you see is really just lead pattern, because the real space net of the absorber is usually larger, units are usually larger than the substrate one. Okay, so you will see a little bit more discussion on the lead optics on the link I gave you, but let me just give you a very quick rundown of what you do in order to obtain a diffraction pattern. So usually, I don't need to go into very detail here. He is showing you a little vacuum chamber, and it has to be done in vacuum, because if you have electron beam, if you have do it in air, you burn out your filament instantly, because air has oxygen in it, and usually the oxygen doesn't like oxygen react with tungsten filament, which is the one that you use to generate electrons. So it must be done in vacuum. Secondly, because you're looking at surfaces, remember, you need good vacuum, otherwise your surface will no longer be clean. So you want to study clean surface, you must do it in vacuum, and indeed ultra-high vacuum. So this is an ultra-high vacuum chamber, and that is the optic that we show a bunch of grid, right, like this. This is called displaced type lead optics, like this, right? So essentially, this part is mounted onto like this, and the electron gun is down here, and the 4 grid that you see here are down here. So the electron gun is concentric with respect to the 4 grid. So you mount it on a flange, called a flange, and then you send your electron beam onto a sample, and you look for a spot on the back side. Your eye will be here, look for a spot on the back side of the optic. So this is known as reverse view optics. So you look at your pattern on the fluorescence screen. You can also, you don't have to do it this way. You can also just you don't need to see the diffraction pattern. You can measure individual diffraction spots. So you really just need a electron gun, right? Electron gun, and you have some device that you can measure the current of the diffraction spot, right? So it's very much like your X-ray diffractometer, where you have an X-ray source, and then you move your detector around, right? This is sort of your detector around to try to pick up diffracted beam intensity, and that's all. Okay. So on the link, so this is called a residual state net or pattern recognition because I just see the pattern. You could, in some optic, you could digitize the pattern. In those cases, you can do more things with what you mentioned. Okay. There is a commercial system sold by Omnicom, other manufacturers sell it as well. The Canadian manufacturer is based in London, Ontario, the OCI. I think there's a link in my website to that. They do sell this. One of the primary, I would say, primary supplier of this type of lead optics in the business right now. You can also do IV curve pattern recognitions, meaning that you digitize. Essentially, you somehow measure this pattern, not just visual inspection, but you try to report this pattern in the old days, by a video camera at the back. Nowadays, you can actually get a digital signal using more sophisticated electronics for this. So in the old days, what you do is that you put a digital camera and just record essentially either this is from the other side, or nowadays you can record from the back side of the gun and actually see the spot you have there and try to digitize it. Okay? And this is what you got, what you see like this. So typically you see spot like this, right? So I'm just trying to show you what you would actually see. And when you change the energy, let's say you lower your energy as much as you can, what you got is just spot. If you lower the energy too much, all the remaining spot will disappear. That means you try to get to the minimum energy. The minimum energy will be the energy that you barely just see one set of spots. So this is my minimum energy. And what does that mean? That means that you just got the first Brillouin zone, right? The first unit cell, if you like, first unit cell in your receiver space net. Okay, so that's why people try to, and all the information really could be contained in the first Brillouin zone. You don't need it to go any further. But if you have more complicated absorbing structure, you do need to go out so that you can see the weaker spot. So for example, if you increase the kinetic energy from 40 volt to 74 volt, you will see more spot coming in. You see this spot, when you increase the energy, what happened? These spots starting to move towards the center because you are increasing the energy. The unit cell, right, the unit vector become bigger, right? So you are seeing. So this is already so here the scale is changing. In other words, the residual vector scale is changing. So these are your original spots, and they are here. And then on the outskirts, you are starting to see more spots coming in. These four more spots coming in. Okay. And then if you continue to do that, sometimes the spot will disappear. So in this case, if you go to 100 electron volt, this thing will disappear. And then if you keep going, you will see more spot again. So you can see, so the spot will come in and out as you increase the size of the residual space. So if you go here, you have the smallest residual space zone. Here you will have the largest residual space zone, which cover more unit cell in residual space. Okay, so you have C more spot. Okay, so that's what yes.
Are there any weak spots in there, or was all?
They are okay. So there should be weak spot because this is a pattern for chromium 100 or 001 1x1 nitrogen atom. So here I think what they're trying to show